the prime numbers have fascinated mathematicians for centuries. And although we know a lot about prime numbers, there's still really basic questions that remain unanswered. And maybe the most famous such question is the twin primes conjecture. Now, as you go along the primes on the number line, as you look at the primes that show up on the number line, you will see that the density of the primes starts to go down. The primes become less and less frequent. And still, there are primes that are quite close to each other that keep showing up. The twin primes conjecture is that there's an infinite number of pairs of primes that are just 2 apart. Okay, and I want to discuss some really beautiful recent work that has made progress towards establishing this conjecture. If there's one thing that we sort of know about the prime numbers, it's that the primes behave like a random set in many senses. The prime number theorem establishes that the number of primes up to n, the density of primes up to n is roughly 1 over log n. Okay. So as you increase n, the primes start to be rarer and rarer at the rate of 1 over log n. And this means that you should typically expect the gap between primes to be about log n, right, around n. But the twin primes conjecture is that you will still find primes, even though they should be rare, that are only 2 apart. Okay. Now, another nice sense in which the primes are random is that if you look at the primes that occur in a particular congruence class, then they are distributed sort of randomly modulo some obstructions, some basic obstructions. So if you write pi of nqa to denote the number of primes that are equal to a modulo q in the numbers up to n, then you should expect that the number of such primes should be close to the total number of primes up to n divided by phi of q. Phi of q, this is the Euler's torsion function. Phi of q is the number of numbers that are relatively prime to q from 1 to q. Okay. So if a and q share a divisor, then there cannot be many primes that are equal to a modulo q. Okay. But if a and q are relatively prime, then you should expect that the primes are evenly distributed among all such congruence classes A. And the number of such congruence classes is phi of q. So this is how many primes you should expect that are equal to A modulo q. And if I write A, E, and Q to denote the error, the maximum over all choices of A, of the deviation from this expectation, then there's a really well-known theorem, the Bombieri-Vinogradov theorem, that says that for all theta less than half and constants A, if n is large enough, then if you sum over all q of these error terms, q going up to n to the power theta, then the total error is smaller than n over polylog in n. Okay. So at least for q, that's a small power of n, we know that the expected number of primes, that the primes do distribute themselves evenly among the reasonable congruence classes modulo q. So that's another sense in which the prime numbers behave like a random set of numbers. All right, so those are some really basic facts about the prime numbers, and we're going to use them in what comes next. The twin primes conjecture, as I said, is a conjecture that there's an infinite number of pairs of primes of this type. And the theorem we now know how to prove is that there's a constant c such as there's an infinite number of pairs of primes of this type, n and n plus c. Okay, so this seems tantalizingly close to proving the twin primes conjecture. And when I saw these results, I thought, what kinds of ideas could lead to this theorem but somehow fail to prove the conjecture? And that's what got me interested. And once I understood all the ideas, these are really beautiful ideas, and it's one of the most intricate proofs that I feel I've ever learned. Okay. All right. In this video, I'm not going to discuss references and assign credit to the people that came up with these amazing ideas. In the description of the video, you'll find links to the references and the history of this problem. Here, I just want to focus on the ideas and try to present the most simplest explanation of what we know, of how we know to establish the theorem. Okay. All right. Before I get started, let's warm up with some really basic tools from number theory. We'll start with the Mobius function. So given a number s, we'll say that it's square free if it has no if it's not divisible by any square, any non-trivial square. Okay, so there's no d squared that divides s. Okay, so a square free number, another way to think about it is just a product of primes. Okay, it's just a product of primes without any prime being squared in that product. Now the Mobius function, an extremely useful function in number theory, is this one. It's defined to be the product over all primes dividing s of -1 if s is square free, and it's 0 otherwise. This is the Mobius function. And a very nice lemma that we'll use over and over again is this one. It says that if a divides b, and you look over all of this, the sum over all s that are in between a and b, meaning that a divides s and s divides b of mu of s, then that's equal to mu of a if a equals b, and otherwise it's 0. Otherwise there's a cancellation. Okay, and the reason is that in this sum, another way to write this, just with the binomial expansion, is what's written on the right hand side. Okay, so there's the primes that divide a. They show up in every term. They contribute -1 to every single term. And for the remaining primes, you can either include the prime, which will give you a -1. For the remaining primes that divide b, you can either include the prime, which will give you a -1, or you can exclude the prime, which will give you a 1. Okay. So this right hand side is equal to the left hand side, and you see that this is just 0, so it's 0 if there's any such prime. Okay, so if b is not equal to a, it's just 0, and otherwise you get mu of a. All right, so that cancellation is extremely useful and powerful, as we shall see. Another really useful function is Euler's torsion function. I've already talked about it, but Euler's torsion function has this formula. We don't need to worry about it too much this version of it too much, because we'll almost always apply Euler's torsion function only to square free numbers. Okay, and for a square free number, Euler's torsion function is exactly the product of all the primes that divide s of p minus 1. Okay, and that's easy to see via the Chinese remainder theorem. Right? The Chinese remainder theorem says that you can count the set prime by prime, and for each prime it's of size p minus 1. And another very useful set of estimates are the so-called Mertens estimates, which say that if you take the sum over all s at most n of 1 over phi of s, and here the sum is over the square free numbers, then this sum is more or less equal to log n. Okay, plus or minus an order 1 error term. And at least one direction of this is not too hard to see. I can show you that the sum is at least something like log n, and that's because if you look at the sum, okay, well, what does it look like? It's the sum over all s of the product of all the p's that divide s, the primes that divide s, of 1 over p minus 1, which I can write like this. And now this thing, I can write it as a power series. Here I'm using the identity 1 over 1 minus x is 1 plus x squared plus x cubed, and so on. Okay. And what I get here is at least the sum over all integers n that are at most n, all natural numbers that are at most n, of 1 over n. Right? Because every such n shows up in the expansion here. And this is just the harmonic series. It's at least log n plus or minus over 1. Okay. So that's why this looks like log n. Okay. And an even more powerful estimate says that if you restrict your attention to those square free numbers that do not have any small prime factors, so let's say L is some parameter, and we restrict our attention to those square free numbers that are not divisible by any prime less than L. Then what you get looks like log n times the product over all the primes up to L of 1 minus 1 over p, plus some error terms that are small. Think of L as a large constant. Okay, and this quantity is the same as phi of W over W, where W is the product of the primes up to L. Okay, again, I'm not going to establish these theorems. These are somewhat classical theorems. I want to talk about how to use some of these ideas to prove the results about that get close to proving the twin primes conjecture. So let me explain how this estimate allows you to also study the sum over all the square free numbers of 1 over s instead of 1 over phi of s. So let's say L is a large number, then the sum over all the square free numbers of 1 over s is at least the sum over all such square free numbers of if I restrict the sum to those that are those numbers that are relatively prime to the first L primes, or the primes up to L. Okay. So this notation, I guess since I haven't discussed it before, this is the GCD. This says that the GCD between S and W is equal to 1. The greatest common divisor between S and W is equal to 1. So if, and once I add this restriction, okay, that's just equal to this, the sum over all such S of the product P dividing S of 1 over P. But 1 over P, I can write it as 1 over P minus 1 minus something that's order 1 over P minus 1 squared. The error term is 1 over P minus 1 squared when I switch 1 over P to 1 over P minus 1. And this is small. It's small because I'm restricting my attention to those primes which are large here, right? All of the primes that show up here are large. They're larger than L. Okay, so now I can write this. This is at least the main term. The main term, the ones that gives you 1 over P minus 1, just gives you 1 over phi of S. Minus the error terms, and the error terms can contribute at most for each prime. You know, every error term has a prime occurring, that contributes 1 over P minus 1 squared. And then some other contribution from the remaining terms. Okay. And this I can bound, the contribution of this part I can bound using the identity 1 plus x is less than or equal to e to the x. So that gives me an expression like this. E to the power of the sum of all of these terms. And this term, it's at most the integral of 1 over x squared, where x goes from L to infinity. So that also I can bound by over 1 over L. So the upshot is that the total magnitude of the error term looks like e to the order 1 over L divided by L. And that's small. That's small as L if you choose L to be a large constant. So what you're left with is the contribution of just the main term that dominates, and that looks like phi of W over W times log n. Okay. So there are two important facts here. First, it says that if you replace phi of s with s, then you can only change the sum by some constant factor. And the second is that if you restrict your attention to square free numbers that only have large prime divisors, then it doesn't matter whether you use 1 over phi of s or 1 over s, you get roughly the same thing. Okay. Next, let's do one more example. Let's try to count the number of square free numbers up to n. That's equal to this quantity. Okay, and one way to count this is that you can, for each a, look at the product, look at the product of all the primes p, where p squared divides a of 1 minus 1. That'll be 0 exactly when a is not square free. And now let's open up this product. Okay. So every term that you get when you open up the product corresponds to a number d with d squared that divides a, and the contribution of that term is mu of d. Okay. Because every prime that you include in d has a minus 1. All right, so now let's take the sum over d outside. So we have the sum over d squared at most n of mu of d. And in the inner sum, we have the sum over all d squared dividing, this is the sum over all a, which are multiples of d squared, and at most n of 1. And now we can estimate this sum. Intuitively, the number of a that are multiples of d squared should be like n over d squared. It's like n over d squared, but this could be off by 1. It could be off by 1. The total amount of error you get if I replace this sum with n over d squared is at most the sum over d squared at most n of 1. The errors could flip the signs of the mu terms. Okay, but the worst case is it makes everything positive. But this sum is at most squared n. Okay, because the number of such d is at most squared n. Okay, that's going to be a tiny term compared to the final term that we'll get. And in the remaining part of our estimate, we have this sum. And now the next thing I want to do is replace it with an infinite sum. I want to remove the restriction that d squared is at most n. So let's throw in all the other d's. And what is the error I get from this? Well, the error is I've added in all of these terms. But these terms are all small because d squared is bigger than n. Okay, so when I do this integral, I get, again, 1 over square root n. And so the total contribution of these error terms is order squared n. All right, so now we're left with this main term, which looks like n times the product of all primes of 1 minus 1 over p squared. Okay, this is again the binomial expansion of this product, gives you exactly this sum. And this product, again using the identity 1 over 1 minus x is 1 plus x squared, and so on, can be expressed like this. It's n times the product over all primes of 1 over 1 plus 1 over p squared plus 1 over p to the 4, and so on. And now we're getting all the squares of the primes here. So this is just the same as n times the sum over all natural numbers of 1 over n squared. So this is a quantity we can estimate very accurately, and it turns out it's 6 over pi squared. Okay. So the square free numbers occur with constant density among all numbers, and the density is this constant. Let's do one final example before we get to the question we're really talking about today, and that's, let's try and count the number of square-free numbers that are relatively prime to the first, the primes up to L. Okay. So I want to do exactly the same, but now I want to restrict my attention to those numbers that are relatively prime to W, where W is a product of the first, the primes up to L. So I follow exactly the same steps, okay, initially, and I end up at this point. And now again, I want to approximate the sum. It should be this time n over d squared times phi of W divided by W. Okay, because these are the number of congruence classes modulo W that are relatively prime to W, or the fraction of them that are relatively prime to W. And again, if you look at the error estimate, you get that it's over squared n. Okay. And then just like before, I will now throw in all of the d's that are even larger than n. Okay, I'll make this sum even bigger and make it an infinite sum. And that also adds a small amount of error for the same reason as it did before. Okay. And then we're left with this number times the product. Now, because the d's here are all relatively prime to W, this sum here looks like the product of all primes that are larger than L of 1 minus 1 over p squared. Okay. And this thing, again, I can estimate it as, this thing is very close to 1. In fact, this whole expression is close to this, and the error term here is this times phi of W times n divided by W times the sum over all primes bigger than L of 1 over p squared. Okay, because every error term that has at least a 1 over p squared contribution from some prime, and everything else contributes, all the other remaining terms contribute at most something less than 1. Okay. But this sum, again, as we've bounded a few times now, is at most order 1 over L. So the upshot is that the error term is 1 over L smaller than the main term. 1 over L times the main term. Okay, so something interesting happens when you look at all of the square-free numbers up to n. Those are, some constant fraction of the total number of numbers up to n. But when you look at the numbers that are relatively prime to W, then the density of the square-free number starts to approach 1. Okay. This is the same, this number here is the same as the total number of numbers that are relatively prime to W. And if you add the additional restriction of those numbers being square-free, it doesn't really change the density by a lot. Okay, so that's kind of interesting. And it's a fact that, well, in some sense, it'll guide some of the intuition that we'll use in the proof. All right, so now let's get to the problems we're discussing today, which is we'd like to prove the twin primes conjecture. Okay, so let's write chi of n to be the indicator function for the primes. Our goal, here's a very basic high-level idea. Let's try and find a non-negative function theta of n with the property that we can prove this equation. The sum for all little n between n and 2n of theta n times chi of n plus chi of n plus 2 minus 1 is greater than 0. If we can do this, if we can show that this holds for all capital N that's large enough, then we'll be done. Because the only way this sum can be greater than 0 is if there is some n in this interval for which n and n plus 2 are both prime numbers. Okay, so that's the very high level approach. intuitively, what we're doing is here is trying to find a distribution on n, on the n in this range, that is likely to hit pairs of twin primes. That's what we're trying to do. And the entire game now is to try to find this theta n, which will be easy, for which it will be easy to establish this equation. Okay. So that's the game, and I'm going to start now with some somewhat natural guess for theta of n. Okay. The way this is going to go is that I'm going to make several attempts at trying to make the proof work. And each attempt is going to fail, and we'll see why it fails, and we'll correct it. And that will eventually get us to the final proof, which I think is quite counterintuitive if you start from it, start looking at it first. Okay, so that's why I want to make some intuitive attempts first. All right, so what do we want to do here? We want to find this theta n, and it should put more weight on the primes. Right, it should be likely to hit a prime. So let's try and achieve that goal first. Let's try and find a distribution on the numbers between, capital N and capital 2 and 2 times capital N, which puts more weight on the primes. And here's a natural such function. Define theta of n to be the product over all the primes dividing n of 1 over p. Times the product of all the primes that do not divide n of 1 plus 1 over p. Where throughout here I'm restricting my attention to those primes p which are at most n. Okay. The intuition here is that if you have a composite number n, it's going to have some prime factors. And so we will significantly downweight its weight in this theta of n by adding these prime factors, and these terms will really boost up the prime numbers. Okay, if you have a prime number n, then it will get additional weight with these terms. Okay, but this choice of theta n has many other nice properties, as I will now show you. So first, what is the contribution of the prime numbers? So what can I say about the sum over n of theta n times chi of n? Well, every prime number has exactly the same contribution, right? Because you just get the product of all the primes in this range of 1 plus 1 over p. And the number of prime numbers, we know by the prime number theorem, is about n over log n. It's very close to n over log n. So the contribution of, so this sum is at least n over log n times this, which is at least n over log n times the sum of all the square free numbers that are less than or equal to n of 1 over s, which we already established is omega of log n. Okay, so this sum is at least omega n. It's proportional to n. Now what can I say about the other terms here? What about the sum of theta n? Okay, over all numbers n. Well, so I can write that like this. It's the sum over all n of the p that divides n of 1 plus 1 over p minus 1. Okay, that's another way of writing 1 over p. Times the product of the p that do not divide n of 1 plus 1 over p. And I did this because something nice will happen now when I expand this out. So when I expand this using the binomial theorem, what is written here? So I can expand this out by choosing a subset of the prime divisors of n. In other words, that corresponds to a square free number s that divides n. And for every prime that I include, I multiply minus 1. Okay, so that gives you mu, gives me mu of s. And all the remaining terms contribute 1 plus 1 over p. All the remaining primes contribute 1 plus 1 over p. The primes I didn't pick. So the result is this sum. The product is over all the primes that do not divide S of 1 plus 1 over P. And this is the key magic that's happening here. This product, suddenly, it depends only on S and not on N. Okay, so you should probably stare at that and try to understand what's going on to get the intuition. And that's very useful because now I'll open up this product as well, and I get the sum over all S dividing N and S dividing T. T corresponds to the set of primes picked in this product of mu of S times S over T. So actually, the set of primes picked in this product corresponds to those primes that are in T but not in S. Okay. You know, I've restricted my attention to S dividing T, so S occurs as a factor of T, and then in the remaining part of T, I've chosen a set of primes that come from this product. All right, this is a nice formula. And what can we do with this? Now let's take the sum over S and T outside and the sum over N inside. And intuitively, this sum, the sum over all N in this range where S divides N, should be approximately N over S. It should be N over S. And that gives a very nice cancellation, because now you see the S's cancel out, and I get this sum, the sum over T of 1 over T times the sum S dividing T of mu of S. But by the property of Mobius functions we discussed before, this sum is 0 unless T is equal to 1. Only when T is equal to 1 is this non-zero. So the only term that contributes here is the term where T is equal to 1, and we get N. So we've made already tremendous progress, because we found a weight function which puts roughly the same amount of weights on the primes as it does on all of the numbers in the interval. And that's great because, you know, the primes occur with density like 1 over log n. So we shifted more mass onto the primes. And that'll help us find primes, hopefully. But there's a problem with this approach. The problem is that the error here is actually really, really bad. Okay, so when I made this approximation, there's a gigantic error. The error could be like, the error could be 1, right? This sum was replaced with n over s. It could be off by 1, and that already gives you an error of the sum over s over t. Here, s and t are square free numbers supported in the primes up to n. And so this sum already, if you look at the contribution, you know, the set of, look at the contribution of st where s is equal to t. That's already like 2 to the power n over log n. Okay, because the number of choices for t is this many. The number of square free numbers that are supported in such primes. So this is a gigantic error term. It's much bigger than all of the other terms. All right. So the approach doesn't work. So here's a second attempt. Let's try and truncate the sum. You see here we had, we had this expression, and we had this nice cancellation. And the issue with the error term here is that t is allowed to be large. Here, let's try and restrict t to be small. Okay, in fact, so let's start with this formula and restrict, t to be small. So that suggests this formula for theta of n, where now I've just restricted t to be smaller than some parameter r. Otherwise, it's actually, corresponds to the formula from before. So it corresponds to truncating the formula we had before to numbers t that show up, which are small. What happens when we consider the sum, the contribution, the weight put on the primes? Well, it looks like this. For the primes, there is no s dividing n. Only one divides and if n is prime. And so the sum looks like this. But that, we've already estimated that the sum over, the sum of 1 over t over all square free numbers up to r is proportional to log r. Think of r here as a small power of n, like n to the 0.1. Okay. So this gives you something that's omega n again. So that's great. And when we apply this, when we try to estimate what happens to the other numbers, do this same kind of calculation that we did before. We take the sum over s and t outside, and then we take the sum over all n that contribute of 1. And now this we can approximate with n over s. We'll look at the error term that shows up in a second. But now what happens, you get again a cancellation between the s terms, and you get this. That's great. And now that t is restricted to being less than r, but otherwise you have the same property before. The sum is over all s that divide t. So once again, the only contribution is from t equals 1. So we're in great shape. And what can we say about the error term? The error term is dramatically better, because now this is a sum over all t that's at most r, and I claim it's roughly r log r. And one way to think about it is that look at every fixed value of this ratio. So look at the value 1. The value 1, for the value 1, there are at most r choices of t. And once you choose t, s is determined as well. Okay, so the 1 shows up in r different ways. 1 over 2 shows up also in r different ways, and so on. So what you get looks like r log r, because it's r times a sum over 1 over 1 over little r over all square free numbers r. Okay, so that's small. If you choose r to be a small power of n, this is small. It's smaller than the main terms here. What's the problem, if you haven't seen it already? The problem is that now our theta of n can be negative, because we've truncated the expression we had before. It may not be non-negative. So the entire approach is defeated. We're not really finding a distribution on the numbers here. There could be cancellations occurring on this side that do not occur for the primes. Okay, and in fact you see that there is no cancellation for the primes. So we need to somehow recover the property that our weight function is a distribution. And a natural way to try and do that is to square the weights. This will make sure that they're non-negative. Okay, so that's what we'll do. So let's take our candidate weights and square them. Okay, and so now we have, as before, this is sum over s and t. And after we square them, we get a sum over 4 variables, s1, s2, t1, t2. Okay, it looks like this. And once again, if you look at the contribution of the primes, then you see that every prime contributes the same. It contributes this quantity, which is proportional to n log squared r over log n. It's something like n log squared r over log n. The non-primes now are going to be a little more complicated because of the cross terms. Okay, but let's see how to analyze this. So if you look at the sum over all n of theta of n, then here's exactly what it is after I've taken the square. So there's a typo here. These should say Sj, Tj. And after you reverse the order of summation, if you take the sum over the s's and the t's first and then the sum over the n's, a natural approximation to do here is to approximate. Now this inner sum here counts the number of n that are multiples of both s1 and s2. And s1 and s2 need not be relatively prime. They may have common factors. So the natural approximation is to approximate this quantity by capital N divided by the least common multiple of S1 and S2. Okay. So that's how we'll approximate it. But now we have a little bit of a problem, because in our earlier calculation, we had that the S1 here canceled out with the S in the numerator here. But now we don't have the product of S1 and S2, but the least common multiple. And to handle this, we need to break the dependency between S1 and S2. Okay. And a nice trick to doing that is what's written over here. You can express 1 over the least common multiple like this. It's 1 over the product times the product of all the primes that divide both S1 and S2. Okay, but this product in the numerator can be expressed like this. And then again, by the binomial theorem, I can expand this product as a sum like this. It's a sum over all R that divide both S1 and S2 of phi of R. Phi of R comes because I'm considering those terms where I pick P minus 1 for each prime, divided by S1 over S2. Okay. So I've now introduced a new variable R, and once I fix R, the dependency between S1 and S2 is broken. It looks again like a product of S1 and S2. And that's really powerful. So let's see what happens when we apply that here. So now we have a sum over this variable R and the S1, S2, and T1, T2 of phi of R times this product. And now the S1, S2 over here canceled out the S's that were in the numerator. Okay, so now we can try to continue as we did before. Let's take the sum over the S's inside. And once again, you see that once you fix R and T, this sum contributes only when the T's are equal to R. If there's any gap between the R's and T's, then there's a cancellation here, and the sum is 0. So the upshot is this quantity is equal to the contribution when both T1 and T2 are equal to R. And that gives you the sum over R of phi of R divided by R squared. Okay, because it's really, in the case that T1 is equal to R, this sum here just contributes mu of R. And T2 also contributes mu of R. So the two mu's cancel out, and what you're left with in the denominator is R squared. Eventually, we're going to actually restrict ourselves to just working with the large prime divisors. All the variables here will only have large prime divisors. And then it won't matter whether you have phi of R here or R. These kinds of distinctions will be irrelevant. They'll just add tiny errors. Okay, but in any case, actually in this particular case, phi of R is at most R. So what's written here actually really is a correct inequality. And so what's written here really looks like n times the sum over R of 1 over R, which is like n log R. So once again, you see we have a win, because the contribution of the primes looks like omega n log n, right? If you think of R as n to the 0.1, this is omega n log n, and the contribution of the non-primes is also about the same order. Okay, so we've managed to put more weight onto the primes. And if we look at the error contribution here, it's similar to what we had before. The error looks like this expression. Okay, I've just removed all the signs. But that's a square. It's a square. It's a sum over S and T less than or equal to R of sum over S T, the whole squared, which is at most R log R, the whole squared. So if R is a small power of n, this error is tiny compared to the main terms that we have here. Okay, so that's it. That's a success, and I think on this page are the key ideas for most of the proof. We've shown how to put more weight on the primes than the rest of the interval. But of course, what we're interested in finding here is not just one prime, but pairs of primes. And to do that, we're going to have to start looking at distributions that take into account both the prime divisors of n and the prime divisors of n plus 2. But the ideas will basically follow, most of the big ideas are, I think, on this page. And then we're going to be using the same ideas in more and more complicated ways. So when we're interested in finding pairs of primes, the natural thing to try and do is, the first natural thing to try and do is to make a weight distribution that looks like this, where you have the same kind of sum as we had before, times the same sum for n plus 2. Okay, this is the sum for n, and this is the sum for n plus 2. And then we square the entire expression to make sure that it's not negative. Okay, so that gives you an expression that looks like this. So now, instead of just 4 variables, s and t, there are going to be 8 variables. Okay, so here I ranges from 1 to 2, and j also ranges from 1 to 2. There are 8 variables. But it turns out that to manage the error appropriately, what we should do is to actually not bound the contribution of each, not bound the magnitude of each t variable separately, but combine the bounds. So we'll take the t, one of the t's for this side and the second t for this side, and bound the product of the t's. Okay, this will give a better handle on the error. Okay, so the actual weight distribution we'll use will look something like this. Now, the approach that I've described here is motivated by trying to find 2 primes, a pair of primes that are 2 apart. But if you think about it, the same approach, it makes sense to try and find many primes that are close together. And eventually it will be productive to do that, even to find just 2 primes. So let's try and generalize the approach a little bit more. So in general, given shifts h1 through hk, think of them as small constants. We can try to find primes at location n plus h1, n plus h2, n plus h3, and so on. Not every choice of shifts h1 through hk is a good idea. Okay, some shifts are unlikely to be simultaneously prime. For example, if there is a prime p with the property that all of the shifts, the shifts cover all the congruence classes modulo p. Okay, for example, if the shifts are 0 and 1, these cover all the congruence classes modulo 2. One of those two is going to be even, right? And either n or n plus 1 is going to be even. Either n plus 1, or n plus 2 is going to be divisible modulo 3. So we need to ensure that the shifts have the property that they do not cover all the congruence classes modulo p for any prime. Okay, to make sure that they're good shifts. And here there are many ways to choose such shifts, but some are less efficient than others. Here's a way that's nice. Set hi to be the k plus ith prime number. Then you see that if you have a prime p that's less than h1, then for every I, hi cannot be equal to 0 modulo p, because hi is a prime number, so it cannot be divisible by p. Okay. So the congruence class 0 is not covered by any of the hi's for such p. And for p that's larger than h1, p must exceed k, the number of shifts. And if p exceeds k, then certainly all of the h's cannot cover all of the congruence classes modulo p. Okay, so this choice of shifts has the property that for every prime, some congruence class is left uncovered. It will also be convenient to ensure that all of the variables that show up in our expression here do not have small prime divisors. This will mean, but by the kind of approximations we did earlier when we talked about square free numbers, if the numbers you're working with do not have small prime divisors, then things like phi of r are more or less the same as r, up to very small multiplicative errors. So it'll be very convenient for us to ensure that all the numbers we're working with only have large prime divisors. So with that in mind, what we will do is, for some L that's much larger than K, let W be the product of the first of the primes up to L. And we will choose a little w with the property that w plus hi is not equal to 0 modulo p for all the p at most L. It's possible to choose such a little w by the Chinese remainder theorem because we can do it prime by prime. For every prime, there is some w with w plus hi not equal to 0 modulo p for that particular prime. And so there's a single w that does the same job for all p that are at most L. So fix such a w. And now we'll choose our weight function to have the property that the weight is 0 unless n is equal to w modulo capital W. Okay. So all of the n's that we're working with here will be in a particular congruence class modulo W. It'll be this congruence class. And this choice will ensure that none of the shifts from n are divisible modulo small primes. Okay, all of the prime divisors of these shifts will be larger than L. Okay, and moreover, if a prime divides one of the variables that shows up here, one of these s's that divides n plus hi, it cannot divide another one because these h's are small shifts, they're close to each other, whereas the primes we're working with here are much larger than k. So we can choose L to be large enough so that all of the prime divisors that show up here in these variables, they only show up for one of the variables, not for more than one. At least only for one of the s's. The t's can share prime divisors, but the s's here cannot share prime divisors in the interesting values of n. Okay. So all of these choices will make the calculations we're about to do much easier to work with because it'll help us approximate quantities by similar quantities. Okay. All right. So now let's start to calculate. Okay. So here is our weight function that we've picked. All of these n's lie in this congruence class modulo W, which has the properties that we discussed. And we proceed just as we did before. So we change the order of summation, write the sum over n inside. And now we want to approximate this sum. The choices we have made ensure that W is relatively prime to all of the variables Sij. And for each of the Sij variables, Si1 and Si2 can share a common factor, but the other variables do not share common factors. So a natural approximation to the number of n satisfying these conditions is capital N over W times the product of the least common multiple of these pairs, Si1, Si2. Okay. If that's not clear, you should think about it. It's just a generalization of what we were doing before. And in this sum, this sum is restricted to those choices of Sij, Si prime, J prime, which are relatively prime when I and I prime are not equal. Okay, because there are no common over here. There is no contribution when the variables share prime factors. These kinds of variables share prime factors. So that's the approximation we'll use, and the error of this approximation is this expression, which once again you can write it as a square. And now it's a little more subtle to evaluate this, the magnitude here. As before, for every ratio that shows up here, that ratio, there are at most r choices for the denominator of the ratio because of this restriction. Okay, there are at most r choices for the denominator. And once you choose the denominator, there are many different ways to choose the variables si, ti. But because all of the numbers we're working with here have large prime factors, the prime factors are bigger than L, the number of possible prime factors is at most log r divided by log L. That's an upper bound on the number of prime factors you can see in these numbers. So the number of ways to assign those prime factors to the variables that we're working with is at most 2k to the power log r over log L. Okay, so that gives you an upper bound on the number of ways to see a particular ratio in the sum. And then once you take into account the overcounting here, what the sum is really looks like log r. Okay, and this number, if L is chosen to be large, k is just a constant here. This looks like r to the 0.01 or some tiny power of r. So the overall sum is bounded by r to the 2 point something small. So the error is bounded in the same way. And here it was crucial that we chose to work with the t's like this. We bounded their products rather than bounding each one of them separately. Okay, this is where that was a powerful choice. Okay, so and next we apply the same trick that we applied before to break the dependencies between these variables s with each other. So we introduce a new variable ri for each sij, and ri must divide sij, and we get phi of ri, just like we did before, and now the dependency between these two is broken, and these si's cancel the sij's that are in the numerator here. So that simplifies things significantly, but we still have a problem. The sij's are not independent of each other quite yet, because we still have the restriction that they do not share prime factors. Okay, which is annoying because that means we cannot take the sum over each of those sij's independently of each other. So to handle this, we're going to have to introduce some more variables. And here's what we'll do. For every pair sij, si prime, j prime, where we want to make sure that they're relatively prime, we'll add a new variable v, ij, I prime, j prime. And we'll take the sum over all such v that divides the greatest common divisor of sij and si prime, j prime of mu v. This is equal to 1 exactly when the two s's are relatively prime and 0 otherwise. Okay, so I add that sum in and add those new variables in. Okay, and now the restriction here just changed to the restriction that the r's, the corresponding r's, are relatively prime. Okay, so these two are the same. I take the sum over all choices of r which are relatively prime, and then the sum over all these v's, and now the s's really behave independently. So let me draw a picture of all the variables here so you can see. Here it is. So we have these r's, and they divide, each r divides a couple of s's. Each s divides one of the t's. And then for every pair of s's that were supposed to be relatively prime, we have this variable v. Okay. So what we're going to do next is we're going to fix all of these variables, the r's and the t's, and look at the sum over the s's, which will cause a bunch of cancellation, just like it did in our earlier attempts. So that's what we do. We take the sum over the r's, sum over the v's. Now, because these v's divide the greatest common divisor is over here, we must restrict the sum of the v's so that the v's are relatively prime to r. Okay. So this is equal to this, and now we've moved the sum over the s's inside, and now the s's really are independent of each other. So what's going to happen? Well, if there's any space here, you know, the s's are forced to be multiples of the r's and the v's that lie below them. And they must divide the t's that lie above them. But if there's any space for the s's to move here, the inner sums will give you 0. So the result is that the only contribution comes from when the t's inside are exactly equal to the least common multiple of all the r's and the v's, the relevant r's and the v's that lie below those t's. Okay, so that's what's written here. That's the only contribution. And in fact, I claim that, although this looks quite complicated, the main term here, the main contribution comes from the terms where the v's are all equal to 1 and the t's are equal to the corresponding r's. This is the dominant term. Okay, that's the key claim. And that's because, okay, if once you have that as a dominant term, then you see that, you know, the only restriction on the r's is that they should be relatively prime. But if I throw in additional r's, if I drop that restriction, I can only make the sum larger. Okay, so I get this nice upper bound on the quantity we're looking at. Okay, so let's talk now about the error introduced in this step. You know, if there is a v that contains a prime factor p that's not an r, then that prime factor occurs twice, at least twice, because the prime factor that occurs here must contribute to both this term and this term, and so it will contribute to at least 2 of the t's. And that prime factor will not be cancelled out by the phi of r expression written here. Okay, so every one of these prime factors that occurs in the v's occurs twice, and that means that you can bound the total contribution of all the error terms here by this expression. So what I've written here is the product of the main term, okay, times the sum over all primes that are larger than L, all of these primes are larger, of 1 over p squared. Now there's also some overcounting that you need to do, because each such prime factor can occur in many different ways in the variables that we have here. There are many different v's, and it can occur in many ways in those variables. But there are only order k squared variables here. So the number of ways in which the prime factor can occur in the variables is at most 2 to the order k squared. Okay, so this term here accounts for all of the error terms. Every error term has at least a 1 over p squared for a large prime p. And then some other combination of potentially p squared terms. Okay. So all of the error terms here are accounted for in this expression. But this expression is small because this quantity, as we've seen before, is order 1 over L. And this quantity, I guess it should say 2 to the k squared over L, okay, but L is much bigger than k squared, so it dominates the contribution of the k squared terms. So the entire thing here looks like something like order 1 over L times something that's comparable to the main term. Okay. Eventually, this quantity will be shown to be comparable to the main term. So this 1 over L will really kill the contribution of the error here. Okay, so that's what happens for arbitrary numbers, or for the numbers in the interval. And now let's look at the contribution of the primes. The analysis is very similar, except that there's one special coordinate. So let's look at the contribution of theta n times chi of n plus h1. Okay, the analysis for all the other hi's will be very similar. Now what happens in the first coordinate? In the first coordinate, there are no variables S1 that divide n plus h1. or they don't contribute anything. So the contribution of the very first coordinate looks like 1 over T11, T12, okay, because S1j is equal to 1. That's the only term that contributes. And the rest, you have the same kind of expression as we had before. Now, as before, we move the sum over the s's inside. And now a good approximation for what's going on here is we can use the Bombieri-Winograd theorem. Okay. To approximate this is counting the number of primes in location n plus h1 that are multiples of all of these Sij's. Now, by our choice of W and the choice of the weight function, the fact that it's in a particular congruence class modulo W, the n plus hi is a congruence class that's relatively prime to every prime that occurs in the Sij. Right? Because every prime that divides Sij must be large. It must be so large that hi is not equal to 0 modulo such a prime. So we can apply the Bombieri-Winograd theorem. We're looking for primes in a congruence class that does not share any common divisor with the modulus we're working with. And the Bombieri-Winograd theorem says, get n over log n divided by phi of W times the product of the phi of the least common multiple of the same pairs that we were working with before. And the error can be bounded by this expression, where this error E, this E is what I introduced right at the beginning as the error in the Bombieri-Winograd theorem for a particular modulus. The modulus we're working with is this one. And I claim that the error is at most n by the Bombieri-Winograd theorem. And let's see why that's true. So here's the error term again. I can group the error terms according to the modulus. So that's what I did here. Just group them according to the modulus. And for each fixed choice of modulus, if you look at this inner expression here, that once you fix Sij, it's the sum over all Tij that are multiples of Sij of this ratio. This expression only has larger terms. Okay, you should think about it if it's not clear. This expression only contains all of the terms that are here. And this one looks nice because it's just log r to the power 2k. And then we need to account for the number of times the number of times these variables show up. And that can be expressed nicely. So the number of choices Sij that satisfies this identity, that can be upper bounded by tau 3k plus 1 of q, where here q is the tau 3k plus 1 of q is the number of ways to express q as a product of 3k plus 1 numbers. The contribution of each one of these least common multiples can be expressed as it's like writing the product of 3 numbers. The 3 numbers are the prime factors that are unique to the first variable, the prime factors that are common with 2 variables, and the prime factors that belong to the third variable uniquely. So that's how you get 3k plus 1. The plus 1 is to handle W. Okay. And now I can apply the Cauchy-Schwarz inequality. There's a trivial upper bound on E and Q, which is n over phi q. Okay, and that's because the number of primes in a particular modulo congruence class modulo Q is at most the number of normal numbers, non-primes that are in that congruence class, and the maximum error you can have for the normal numbers is at most n over phi q. So that's an upper bound. So applying the Cauchy-Schwarz inequality, I get these bounds, where now I have here tau 3k plus 1 q the whole squared, and the square is at most tau 6k plus 2 q. Okay, the number of solutions here squared is at most the number of solutions when you partition into 6k plus 2 variables. Because every partition in 6k plus 2 variables can be thought of as a partition on the first and a partition on the second. Okay. If that's not clear, spend a few minutes to think about it and figure it out. And what you're left with then is this expression, the first term here, can be bounded by the Bombier-Vinogradov theorem like this. And the second term here, once you take the n out, there's a squared n here, which is combined here. The second sum here is at most the sum over u at most r squared of 1 over phi u to the power 6k plus 2. Because when you do this expansion, each term that shows up here will show up tau 6k plus 2, at least tau 6k plus 2 times. Okay. So there are many clever ideas happening in this analysis, but it's really beautiful. But the upshot is that this log term is enough to kill everything else that's showing up here. Okay, so we get something that's less than n. So that handles the error. And now we're left with main term looks like n over phi of w times log n. And we have an expression very similar to what we had before. And as before, we need to break the dependence between these two, which we can do in analogous fashion to what we did before using this fact. Okay, so you can introduce a new variable r, and the function g of r is a multiplicative function which on primes takes the value p minus 2. Okay, that breaks the dependency between the s1 and s2. And so we get this expression. This is not quite exactly what we saw before because there's no cancellation. Earlier we had Sij here and Sij here and they cancelled out. Now we don't have a cancellation, but we're working with large primes. So this is more or less 1. Okay, that's the intuition. And we'll see how it'll work out to be 1. Okay, so now we've reached the stage where we have this formula. And we can now move the sum over the s inside because we've broken all the dependencies between the s's. And this time we don't have a perfect cancellation here. Now before we had Sij divided by Sij, and those became 1, so that made it a little bit easier. But we can still evaluate the sum explicitly using the binomial theorem. It looks like the product over all the primes that are in Tij but not in the variables below of 1 minus p divided by p minus 1. And the point is this product here, this quantity here is order 1 over p. Order 1 over p. And so I claim that actually, just like before, the main term is the one where all the v's are empty. They're 1. And the t's are equal to the r's. And that's because every prime that shows up either in a v or in the t that's not in the r contributes to 1 over p squared. If a prime shows up in t but it's not in any of these variables below, then there's a 1 over p contribution from here and a 1 over p contribution from here. Okay, so that contributes 1 over p squared. If there's a prime here, then it's similar to what we saw before. There's again a 1 over p squared contribution because it must contribute to both sides. Okay. So the upshot is we can bound the error of dropping all such terms like this. And that's again small compared to our main term. It looks like we can bound it by, for each prime we have a contribution of 1 over p squared times some number that depends on the number of variables here, because there are different ways to arrange this prime among the variables. Okay, so this expression here is an upper bound in all the ways to have terms that with 1 over p squared contribution, and that's small. It gives a 1 over L because all of the primes here are larger than L. So the main term now looks like this. right? Where the sum here is over all choices of R that do not share any prime factors. And we can actually approximate that by dropping the restriction that the R's do not share prime factors, because once again, if there is a prime factor that's common to two R's, then that prime factor shows up with a contribution of 1 over p squared. So by similar calculations to this error, we can throw in addition, the terms that come from where there's no restriction on the R's being relatively prime to each other. And that's only a tiny error. That's a 1 over p squared error compared to our main term. Okay, so I haven't shown the calculation for that here, for this approximation, but it's very similar to this. All right, so the upshot of all of these calculations is that the contribution of general numbers looks like n over w times this kind of expression, the sum over all r's whose product is at most r of 1 over r. And the contribution of primes in a particular coordinate looks like this kind of expression. And the win here is that the primes have, an additional factor. They're a product of k numbers here, and here there's a product of k plus 1 numbers. And that corresponds to an additional factor of log r. Okay, that we're eventually going to get up. But it's a little bit annoying because we have to deal with this correlation among the variables somehow. And there's a nice way to do that. So recall that we talked about this theorem right at the beginning. It says that the sum of the square free numbers that are relatively prime to w of 1 over phi of s is very close to this quantity, log r times the constant, which is phi of w divided by w. And a corollary of that is that if you have any function f from 0, 1 to the reals, then this sum with weights f of log s divided by log r. Suppose you weight every s here by f of log s divided by log r. It looks like this main term here times the integral of f going from 0 to 1. That's a claim. And this more or less follows from this theorem above, because I can, if f is nice, if it's sufficiently smooth, then I can break up the set of square free numbers that go up to r into, say, capital K intervals. Each one corresponds to s lying between two powers of r, two subsequent powers of r, I minus 1 divided by k and I over k. And if in each one of those intervals f is, roughly a constant, okay, then this is approximated by this sum. But each one of these sums I can approximate using the main theorem, right? As the sum over all s in this interval is equal to the sum up to the endpoint minus the sum up to the initial starting point of the interval. So that's what's written here. And when you do that calculation, you end up with phi of w log r divided by w times the sum of f of I over k divided by k. Okay, so this looks like the integral of f. Okay, I'm just giving you a sketch for why this is true. So this is helpful because now we can evaluate this product as the main term looks like phi of w times log r divided by w to the power k. And what's written inside here is the integral of f, where f is 1 when the sum of the variables is at most 1 and 0 otherwise. Okay. You can take the sum and evaluate it term by term, and each term applying the corollary from before will give you these integrals. And similarly, we get the same kind of expression from our bound for the contribution of the primes, except the integral now, the innermost term looks like the integral with one of the variables squared. Okay. All right, so the upshot of all these calculations is the main term here, this term is identical for both the general interval and the primes. The only difference is in this term. And this quantity, the quantity up here in general is larger than this quantity, but this quantity will show up k times, right? Because we'll be taking the sum over the k shifts. Okay, so we could potentially get a win here. However, we have the strange constraint that we need to satisfy, that f should be supported only on points in the simplex. All right, so let's try and now evaluate these integrals. Okay, and then there's a nice way to do that. It's basically what we're trying to do here is calculate the volume of the simplex. And a nice observation that's helpful is that we can generalize f to be to fz. The f we were looking at before is f1, but fz we write as the same expression, the sum of the x's is at most z. Okay, and that corresponds to a change of the variables, where we replace each xi with xi over z. Then you see that what we're trying to calculate is v1k, this integral. It's one of the things we want to calculate. But in general, we have that vzk is equal to z to the k minus 1 of v1k, because it's a change of variables where we're dividing by z. Okay, so that allows us to calculate v1k, because v1k is this integral here on the outermost variable, because for each choice of xk, the constraint on the remaining variables looks like the sum of them is at most 1 minus xk. Okay. And so that gives us this formula in terms of k, which evaluates eventually to 1 over k factorial. And the same kind of calculation for the other integral gives us 2 over k plus 1 factorial. Great, so now let's plug that back into our estimate. We really like to show that this quantity is positive. We've given these approximations. And so what we really want to show is that this ratio is bigger than 1. But this ratio, I said earlier that the main terms are the same, but that's not quite right. The main terms, the second main term has a log r, and the log r over log n, which the first main term does not have. So the ratio between these two looks like log r over log n times this quantity, which is log r over log n times 2k over k plus 1. Okay, so even if you take k to be large, the best we can hope for here is a factor of 2, which is not going to be good enough to get a win, because we want here this ratio to be bigger than 1. So we need one more idea. It's the last idea that we'll need, and that idea is to use not the uniform weights on the simplex, but some other weight. Okay, so in general, we'll weight t1 through tk according to some function f, which is supported on the simplex. Okay, and we'll choose f so that its magnitude is at most 1. Okay, and we'll add these weights into our expression for theta. So every t1 through tk will be weighted according to w. And now what happens? Well, all the calculations we've done before work out pretty much the same. So everywhere here we'll have w. Okay. I didn't write it out. All of the error terms do not involve w, because the magnitude of w is at most 1. So all of the error terms apply as is. And the end result that you get is, in the case of this calculation, there will be a w squared. Okay. In the case of the primes, you'll have here, again, w of t1. In the final expression for the primes, well, let's just look at the final result. So this is what ends up happening. So in the case of arbitrary numbers, you have f squared written here. Okay. And in the case of this f squared comes from the place where we took t11, t12, and multiply the two of them together. So there's a squaring of the weights happening there when both of them are equal to r. And in the case of the primes, what we get is that the innermost integral is the integral squared, and the rest of it is the integral, or all the variables. And now our new goal is to find some symmetric function f that will make this ratio large, right? Make this ratio larger than 1. And we can do it explicitly. So it turns out, so if you set capital F to be this function, this product function, and set f to be the truncation of f to the simplex, this product function can take values that are larger than 1, but it'll be nicer to use this. We can, everything here, this condition really doesn't matter, because eventually we're taking the ratio of two things that depend on f. If you scale f, you can always, if you find two f's that have a good ratio here, if you find an f that gives you a good ratio here, you can then scale that f so its magnitude is at most 1 and the ratio will be preserved. Okay, so it'll be convenient to work with this capital F where it takes values that are bigger than 1, because I've chosen the normalization here so that this integral is equal to 1. And so I can think of f squared as a probability distribution. Okay. So you can check that with this choice, where here b is a parameter that's roughly order k log k. Okay. But with this choice, f squared becomes a probability distribution. And moreover, the expected value of xi looks like log b over b. The expected value of xi squared is like 1 over b. Okay, I've done all the calculations here. I'm not going to go over them in this video, but you can check them for yourself. And that means that the variance of each variable xi is small. The variance is 1 over b. And so the variance of the sum of the variables is, you should say here, k minus 1 times the variance of x1. But it's, in any case, order k over b. It's small. And that means that the probability that the sum of these variables exceeds, say, 1/2 is small. By Chebyshev's inequality, you can bound this by order 1 over log k, where it's really bounded by the numerator here because the denominator is some constant, and the numerator is order 1 over log k by a choice of b. So the upshot is that now we've normalized it so that the integral of f squared is 1. So this means that the integral of little f squared can only be smaller. It's a truncation of f, so it's also at most 1. Whereas the other term that we care about, we can approximate it with this, the integral where the innermost integral goes from 0 to half, and that works out to be something like log squared log squared b divided by b squared, divided by b, log squared b divided by b. And the actual integral we care about is close because this is a probability distribution, so the error term, this thing is at least the contribution of this integral times the probability that x2 through xk are at most half. When x2 through xk are at most half, the inner integral here will contribute exactly the same as what f contributes. And this probability is very close to 1 because of the variance calculation. So the whole expression here is proportional to log squared b over b, which is like log k over k. And putting this back in, this gives us a ratio here of at least log k. Okay, and then now suddenly we have a win, because that is a constant that we can make larger and larger and eventually make this to be bigger than 1. All right, so that's the end of the video. I've tried to show you the main ideas that go into showing this recent amazing work, proving that the gaps between the primes, there's a constant C for which the gap of C shows up infinitely often between prime numbers. I hope you enjoyed it.